Hello, can you hear me?
Yes, sir. Yes, sir.
Okay, so we will wait for a few minutes more and, and then we will start at 7:10.
Okay, sir. Thank you, sir.
Okay. You can see the slide. Can you please confirm whether you can see the slide or not? I am sharing my screen currently. Okay, so let's. So, hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will be. So I welcome you all for this 12th interaction session on the course Experimental Physics 1, which is being taught by NPTEL this July 2025 session with course code NOC 25 PH51. So today we will be solving a few problems that will be based on week 12 course contents or week 12 lectures of the course, uh, and that will help you to solve your this year's assignment problems as well as sample problems that might come in the exam. So let's first discuss briefly about the concept that was covered in this week's lecture. So if we talk about week 12, so in week 12 the lectures was about, so it was about mutual inductance, then uh, about permeability of air, where the theory was explained as well as the experiment was performed to calculate the permeability of air. Then discussion about devices around us, for example, electric fan, grinder, drilling machine, and the most important component in all of these devices is the electric motor, and the working principle of electric motor was also discussed. Then another device which is called as vibrating sample magnetometer, that was also discussed. Vibrating sample magnetometer. So if we discuss about mutual inductance, so mutual inductance is the property it is the property due to which if the two coils are in proximity to each other, then the change in magnetic flux in one coil produces the EMF in secondary coil due to the property. So in general, it is written as, so mutual inductance given by M, which is equals to N2 by N1 phi 21 divided by I1. So how this is coming? Uh, so now let's first discuss the notation. So here N2 is the number of coils, number of turns in coil 2. Similarly, N1 is the number of turn in coil 1. And what is I1? I1 is the current flowing in coil 1. And what is phi 21? So phi 21 is the flux, the change in flux or flux in coil 2 due to the current I1 flowing in coil 1. So flux in coil 2 due to I1 in coil 1. So this is the expression for mutual inductance. And if you talk about the induced EMF in coil 2, so E2 is given as minus M di1 by dt, and similarly E1 also can be written as minus M d I2 by dt. So if the two coils are here, so it will be having same mutual inductance for coil 1 and coil 2. And if there are two coils having self inductance L1 and L2, then what will be the mutual inductance of the two coils? So it is given by M equals to K root over of L1 L2, where K is called as coupling coupling constant. Now, if we try to derive how the expression for EMF we are getting, so we know, suppose the current I1 is flowing, and there is number of turns of the coil is N2, and the number of turns in the second coil is N2, and so the flux which will be associated with the coil 2 due to the current in coil 1 will be given by N2 phi 21, and it will be direct proportional to I1. Then according to the proportionality constant and the property of the coil, so it will be N21 equals to M into I1. Again we know the induced EMF is given by, suppose the induced EMF in coil 2 is given by minus d by dt into change in flux. Change in flux in coil 2 is N2 phi 21, and this N2 phi 21 is equals to Mi1. So we can write d by dt of Mi1. So it becomes E2 equals to minus M d I1 by dt. This is the expression. So similarly, we can write E1 equals to minus M d I2 by dt. So this expression that we are getting, this expression. Now, if we discuss about the permeability, so what is permeability? Here, permeability means magnetic permeability. Permeability is magnetic permeability. And what is the significance? Basically, it shows how easily magnetic flux lines can pass through a medium. So, it's basically explains how easily magnetic field lines can pass through a medium, which is called as magnetic permeability. And we know the magnetic permeability of free space is given by mu 0, and its value is 4 pi into 10 to the power minus 7 Henry per meter. And that's why the magnetic field intensity is given by the relation B equals to mu H. When mu is equals to 1, then B equals to H. Depends upon whether the material is present in a, so it depends upon the medium. And if you talk about the vibrating sample magnetometer that was also explained, basically this vibrating sample magnetometer, it works on the principle of Faraday's law of electromagnetic induction. So the and it is basically used to study the magnetic properties of the materials. That is, we know depending upon the magnetic properties, materials are classified into three types: diamagnetic, paramagnetic, and ferromagnetic. So these type of materials properties that can be studied through this vibrating sample magnetometer. So the sample is placed in between the two pickup coils, and it is vibrated. So when it is vibrated, so the flux associated, since the surface area changes, the flux also changes, because flux is magnetic field intensity into flux is equal to b dot a. So the since the area changes, that is the component of the area along the magnetic field changes due to the vibration, so it produces magnetic flux, and due to that magnetic flux, the change in magnetic flux produces induced EMF, and from those induced EMF we can study the properties of the magnetic materials. So that was also discussed. So now let's solve a few problems based on these concepts. So this is the first problem of today's interaction session. It says the number of turns in the primary and the secondary coil of an ideal transformer are 100 and 250 respectively. If the current in the primary is 5 ampere, then what will be the current in the secondary? The options are option A 8 ampere, option B 4 ampere, option C 2 ampere, and option D 1 ampere. So it says there is a transformer, and we know in a transformer there are two coils, primary coil and secondary coil. So when flux changes in primary coil, then EMF is induced in secondary coil, and that's the principle of step up and step down transformer, because when the number of turns in the primary coil is less than the number of turns in the secondary coil, then it is called as step up transformer, and when it is reverse, it is called as step down transformer. If the number of coil in a primary coil is more, then it is called as step down transformer. So but here the condition is it is an ideal transformer, and it has two coils, and the number of turns is, suppose number of turn in coil 1 is N1 100 and N2 number of turns in coil 2 it is 250, and the current in the primary coil is given. So the induced current in the primary, so we know due to the phenomenon of mutual inductance, the change the current, we know if a conductor carries current, it produces magnetic field. So when so depending upon the magnetic field produced, so it will get affected in the secondary coil, and then there will be induced EMF, and that induced EMF will again cause a current in the secondary coil. So we want to find out that current. So I'll give you a few minutes to solve this question and to find the correct answer, and then we will discuss. So I will request, if you are not speaking, then you can mute yourself. Only in case you are speaking, you are saying something or you are asking something, then you can unmute yourself and then speak to me. Actually, this will ensure to have no background noise. So can you tell me what will be the correct answer? So in case of so in the question it is mentioned there is so number of turns in the primary and secondary coils of an ideal transformer. So what is an ideal transformer? For an ideal transformer, there is 100% efficiency. So there is no power loss. So in that case, power in primary coil is equal to power in secondary coil. So power in primary is equals to power in secondary. So that implies VPIP equals to VSIS. We know power is given by voltage into current. Here P is primary, S P means primary and S means secondary. So what will be IS? IS will be VPIP divided by VS. So in the question, uh, there is no value of voltage, but we have number of turns. So how we can determine the uh, ratio? So it is Vp by Vs into Ip. So in case of a transformer, this E1 is directly proportional to N1, E2 is directly proportional to N2. That implies E2 by E1 is equals to N2 by N1. So this E2 by E1 again is equal to V2 by V1. So V2 by V1 is equals to N2 by N1. So that implies Vp by Vs will be number of turns in primary coil divided by number of turns in secondary coil into Ip. So Is is in primary coil it is 100 and secondary it is 250. So it is 100 divided by 250 into 5 ampere. So it is 2.5 divided by 5 divided by it is 2 ampere. So the correct option is option C, that is 2 ampere. So the depending upon the number of coils, so since here the number of coil is more in secondary, number of turns are more in secondary coil, so the current will be lesser because there is no power loss. Input power is equal to output power, so the current that will be flowing will be lesser in case of coil having maximum more number of turns. Is this clear? Okay, now we'll move to question number 2. So question number 2 says a straight conductor of length L carrying a current I is bent in the form of a semicircle. The magnetic flux density in Tesla at the center of the semicircle is, options are option A mu 0 pi I divided by L, option B mu 0 pi I divided by 4L, option C mu 0 I divided by L, or option D I by L. So this question is related to the concept of uh, magnetic field due to a current carrying conductor. So similar types of problem we had discussed in the last introduction session also. So this question is based on that concept. So there is a straight conductor. Suppose this is a straight conductor and its length is L. Now we will bend this straight conductor into a semicircle. Suppose this is the center and we bend that into a semicircle. So this overall length, this is L. Then we need to find the magnetic flux density at the center of this semicircle. So at this point P, we need to find the magnetic flux density. So I'll give a few minutes to try to solve this question and then we will discuss. So, for a straight conductor of length L, the magnetic field intensity is given by the expression B equals to mu 0 I by 4 pi L by R square. This is for straight conductor of length L. Now, this length L, when we bend it to a semicircle, then we know the total perimeter of a semicircle is pi r. So, pi r equals to L. That implies r equals to L by pi. So, what will be the value of magnetic field B? So, it will be mu 0 by 4 pi into, so mu 0 I by 4 pi L by r square. It will be mu 0 I divided by 4 pi into L divided by r square, means L by pi square. So it will be mu 0 I divided by 4 pi into L into pi square divided by L square. So L, 1 L gets cancelled out, 1 pi gets cancelled out. It is mu 0 I, mu 0 pi I divided by 4L. So that will be B mu 0 pi I divided by 4L. So the correct option is mu 0 pi I divided by 4L. That is option B. Is this clear to you? So we know this is the expression for a straight conductor of length L. So when we bend it to a semicircle, then the length remains same. So this becomes pi r. So what is the distance? So this is r, and this L is equals to pi r. So we calculated and we got mu 0 pi I by 4L. Now we move to question number 3. So question number 3 says, in the hysteresis cycle, the value of H needed to make the residual magnetism to 0 is called option A retentivity, option B coercive force, option C Lorentz force, or option D none of the above. So this is related to the hysteresis cycle. This is a conceptual question. So I will give you a few minutes and then we will briefly discuss about this hysteresis loop and we will find out the correct answer. That is, what is the so the value of H which is needed to make the residual magnetism to 0. What it is called basically. So let's discuss about hysteresis loop. So what is hysteresis cycle? So hysteresis cycle is basically made for a ferromagnetic material. So when a ferromagnetic material is magnetized and demagnetized, then there is a loop that is formed to through which we can calculate the magnetic energy stored in that material. So how it so for an for a mm, ferromagnetic material. So hysteresis loop it is drawn. So this is the so along x-axis, if we take magnetic field in H and it is B. So when H is increased, so first B increases rapidly and then it saturates. But when it is decreased due to the uh, uh, permanent magnetization, since it is a ferromagnetic metal, it is magnetized. So when it is again decreased to zero, then it does not. So it is the direction when we are increasing h, but when h is changed in the reverse direction, the curve uh, does not follow its original path. However, it goes like this. So in this way, here the point at which the value, so when although we have h is 0 here, there is some remanent flux, so this is called as Br, that is remanent flux density. And then in order to make it further 0, we need to reduce the value of h in opposite direction. This is called as coercivity. So this is the then it goes to negative saturation, and then when it is increased, then it becomes like this. So this is called as hysteresis loop. Hysteresis loop. So this is called as Br. Similarly, this is minus Br. Then this is minus Hc. This is Hc. So Br is called as remanent flux density, and Hc is called as coercivity. Coercivity. So the value of H needed to make the residual magnetism 0. So this is the value of H which is needed to make the residual magnet. So this was the residual magnetic field which is non-zero. So in order to make it 0, we the value of H that is needed is called as coercive force. So the correct option is option B. Now we move to question number 4. Question number 4 says a galvanometer having resistance 20 ohm, it is converted into an ammeter by connecting a 5 ohm shunt resistance across it. In order to double the range of this ammeter, the additional shunt resistance to be connected across it is, options are option A 3 ohm, option B 2.5 ohm, option C 4 ohm, and option D 5 ohm. So this question is related to the concept of moving coil galvanometer and how this moving coil galvanometer can be converted into voltmeter and ammeter. So here the galvanometer has a resistance of 20 ohm and it is converted into an ammeter by connecting a 5 ohm shunt resistance. And in order to double the range, so in order to, if you want to make the ammeter range twice of that initial range, then what is the additional shunt resistance that need to be connected across it? So these are the 4 options. I'll give you a few minutes to solve this question and then we will discuss. So we know uh, a moving coil galvanometer, it can be converted into an ammeter by connecting low resistance shunt, that is low resistance in parallel. So initially it was 20 ohm and we connected another low resistance of 5 ohm. So this whole combination, the current, suppose I passes through, then what will be the resultant resistance or equivalent resistance? So R, we know 1 by R equals to 1 by 20 plus 1 by 5. That implies R equal to 20 into 5 divided by 20 plus 5. So 100 by 25, it is 4 ohm. So 4 ohm is the overall combination. So this galvanometer now, suppose this is the galvanometer, it has 4 ohm and its range is or full deflection is I. Now we need to convert it into an ammeter of twice of its range. So I we need to convert into 2I. So 2I means additional current should pass through the shunt resistance. So now this is galvanometer, then there is an additional resistance shunt and current 2I. So as always I passes through G and then another I it passes through the shunt resistance S. So when same current is passing, so for a for a parallel connection we know V is equals to constant. Suppose this is Ig, this is Is. So that implies G into Ig equals to S into Is. Now what is the value of G? G, it has the resistance of 4 ohm. So 4 ohm into I equals to S into I. That implies S equals to 4 ohm. So if we connect the connect an additional 4 ohm resistance, then the range will be twice. Now if the question was uh, to make I to 3I, then in that case what will happen? So the uh, so this is G. So current I will pass through G and current 2I it will pass through S. So in that case I into 4 equals to 2I into S. S will be 2 ohm. So larger is the current range you require, lesser will be the resistance that will be connected in parallel, because lesser is the resistance, more current will flow through that branch, so that the current flowing through the galvanometer that remains the same. And that's this is the way to convert the to change the range of the galvanometer, range of the ammeter. I hope this is clear to everyone. Now we move to question number 5. So question number 5 says, if a current of 2 amperes flowing in the primary coil is reduced to 0 in 0.05 second, then the induced EMF in the secondary coil is 50 volt. Then what is the mutual inductance between the two coils? So there are two coils. So there are two coils and this is the core. This is primary coil, this is secondary coil. So this is a current in the primary coil which is flowing and it becomes 0. So 2 to 0 within 0.05 second. Then what will be the induced EMF in the secondary coil? Sorry, the induced EMF in the secondary coil. So the EMF induced here is 50 volt. Then what will be the value of mutual inductance? Then what is the value of mutual inductance? So this is the question related to the concept of mutual inductance. So I will give you a few minutes and then we will discuss. So we know, as we have already discussed, the induced EMF is given by M di by dt. So what is di by dt? So di by dt is equals to I2 minus I1 divided by T2 minus T1. So current changes from 2 to 0 in 0.05 second. So 2 minus 0 divided by 0.05, that implies 2 divided by 0.05. So M will be equal to E dt by di, that implies E into 0.05 divided by 2. So what is the value of E? E is 50 volt. 50 into 0.05 divided by 2, so it's 25. So M is 1.25 and the unit is Henry. So the correct answer is option B, 1.25 Henry. I hope this is clear to everyone. Now we move to question number 6. So question number 6 says a long solenoid of length 100 centimeter and cross section 10 centimeter square having 500 turns has wound about its center a small coil of almost same cross section of and of 4 and of 40 turns. Calculate the mutual inductance between the coils. So there is a long solenoid of length 100 centimeter and cross section is 10 centimeter and it has 500 turns and it has wounded over about a small coil of same cross section and 40 turns. Then calculate the mutual inductance between the two coils. So I'll give you a few minutes and then we will discuss. The options are option A 25.13 microhenry, option B 27.45 millihenry, option C 7.54 millihenry and option D 0.25 millihenry. So there is a long solenoid. The length is 100 centimeter and cross section is 10 centimeter and it has 50 turns. Then another small coil is present inside which has the same cross section and of 40 turns. Then what will be the mutual inductance between the coil? I'll give you a few minutes and then we will discuss. So the formula for mutual inductance is given by M equals to mu 0 NP NS and A. So both have same area. So where NP is the number of turns per unit length, that is 500 for primary, and NS is the total number of turns in the secondary coil, which is 40, and the area of cross section is 10 centimeter square. So NP, it is 500 divided by 100, that implies, sorry, it is 500 divided by 100, this is 100 centimeter. So this is 500 by 1 meter, which is 500. So this is number of turns per unit length, and ns, it is the number total number of turns in the secondary coil, it is ns is 40, and area a is 10 centimeter square, that implies 10 into 10 to the power minus 4 meter square, which is equal to 10 to the power minus 3 meter square. Now mutual inductance m is 4 pi into 10 to the power minus 7 into 500 into 40 into 10 to the power minus 3, that implies 4 pi into 5 into 4 into 10 to the power minus 7 Henry, which is equal to 20 to 51.3 into 10 to the power minus 7 Henry, which is equals to 25.13 microhenry. So the correct answer is 25.13 microhenry, that is option A. I hope this is clear to everyone. This was a straightforward question provided you know the exact formula. So this was the formula mu 0 NP NS into A, where NP was the number of turns per unit length, NS the total number of turns in the secondary coil. That's why it is noted as small n and this is capital NS, and A is the area of cross section. So if you put all the value, you can get the answer. Now question number 7. Question number 7 says a current of 25 ampere flows through each of two parallel wires separated by 2 centimeter. Calculate the force exerted per unit length of each wire. Options are option A 0.025 Newton, option B 0.00625 Newton, option C 0.075 Newton, and option D 0.25 Newton. So it is mentioned a current of 25 ampere flows through each of the two parallel wires separated by 2 centimeters. So it is separated by 2 centimeter. There are two parallel wires and current of 25 ampere that flows across the two wires. Then what should be the force exerted per unit length of each wire? These are the options. I'll give you a few minutes and then we'll discuss the correct answer. So the force per unit length between two conductors carrying current I1 and I2 and separated by a distance d, it is given by the formula F equals to mu 0 by 4 pi 2 I1 I2 divided by d Newton. So it is mu 0 by 4 pi into 2 into, so here I1 equal to 25 ampere, I2 also equals to 25 ampere, and d is 2 into 10 to the power minus 2 meter. So 22 into 25 into 25 divided by 2 into 10 to the power minus 2. That implies this is, so mu 0 by 4 pi is 20 to the power minus 7. So it is 625 into 10 to the power minus 5 Newton. So F equals to 625 into 10 to the power minus 5 Newton, which equals to 6.25 into 10 to the power minus 3 Newton. That is 0.00625 Newton. So this is the answer. So 0.00625 Newton. Correct answer is option B. Now we move to question number 8. So question number 8 say is what is the dimension of intensity of magnetization? So these are the options: m0 l minus 1 t0 a, m1 l1 t0 a minus 1, m0 l minus 1 t minus 1 a, or m minus 1 l t0 a minus 1. So what is magnetization? So magnetization, intensity of magnetization is defined as magnetic moment per unit volume. So intensity of magnetization, that is m, it is given as magnetic moment per unit volume. Magnetic moment per unit volume, and magnetic moment is given by mu is equals to I into a. So current, so the magnetic moment of the current loop is given by the current flowing through that loop and the area cross section. So current into area. So I, the if you talk about the dimension, so for I it is a and area it is L2. So that will be the dimension for m. It will be uh, L2 into a divided by L3. So it is m0 l minus 1 t0 a1. So m0 l minus 1 t0 a1, that is option A. So the dimension of intensity of magnetization is m0 l minus 1 t0 a, because the intensity of magnetization formula is magnetic moment per unit volume. Magnetic moment is current into area. Area is length square into current is ampere a, then by L cube. So this is the correct answer. Now we move to question number 9. Question number 9 says the magnetic susceptibility Xi is negative for option A ferromagnetic material, option B paramagnetic material, option C diamagnetic material, or option D it is positive for all of para and ferromagnetic material. So basically what is susceptibility? So susceptibility is defined as the ratio of magnetization divided by the magnetic flux intensity. So it is given as m by h. So it is negative means when it suppose the a material is placed in a magnetic field and it is magnetized in opposite direction to that of the magnetic field, then it will be, the susceptibility will be negative. So uh, um, what are the magnetic materials? So there are three types of materials depending upon the magnetic property: uh, ferromagnetic, paramagnetic, and diamagnetic. So diamagnetic are those materials for which the magnetic moment is produced in opposite direction of the applied magnetic field. So H is the applied field and M is the magnetization. So when direction of M and H are opposite, then it is negative. So for diamagnetic materials, they are magnetized in opposite direction to the applied magnetic field. They are magnetized in an opposite direction to the applied magnetic field. That implies Xi is negative for diamagnetic material. So the correct option will be option C, that is diamagnetic material. Now we move to question number 10. So question number 10 says a transformer connected to 220-volt line shows an output of 5 ampere at 440 volt. The efficiency of the transformer is 100%. The current drawn from the line is, options are option A 5 ampere, option B 10 ampere, option C 15 ampere, and option D 11 ampere. So that the transformer, it is connected to a 220 volt line and output is 5 ampere at 440 volt. Then what is the current drawn from the line, and the efficiency is 100%. So these are the four options: 5 ampere, 10 ampere, 15 ampere, and 11 ampere. So I'll give you a few minutes to try to solve this question, and then we will discuss about the correct answer. So at the beginning of our interaction session, we solved a problem in which it was mentioned about ideal transformer, and ideal transformers have 100% efficiency. So for 100% efficiency, VPIP is equals to VSIS. That implies what is IP? IP is VSIS divided by VP. So IP is 440 into 5 divided by 220. So 10 ampere. So the correct answer is option B, 10 ampere. So when um, uh, a transformer is connected to a 220 volt line, then if its output is 5 ampere at 440 volt, so means its uh, input power is equal to input power, it is equal to output power. So that means VPIP equals to VSIS. So we calculated IP is equals to VSIS divided by VP. So this is the correct answer, that is option B, 10 ampere. Now we move to question number 11, which is the last question of today's interaction session. So yes, the working of dynamo is based on the principle of, options are option A, electromagnetic induction, option B, conversion of electric energy into mechanical energy, option C, magnetic effects of current, and option D, heating effects of current. So working of dynamo is based on the principle. So these are the four options. You need to find out what is the actual working principle of of a dynamo. So I'll give you a few minutes and then we will discuss briefly about the working principle of a dynamo, and then we will determine the correct answer. So, if we discuss about the operation of dynamo, basically dynamo is a device which produces mechanical energy into electrical energy, mechanical energy to electrical energy. So, it is used to produce electrical energy from mechanical energy. So, dynamo basically it has a coil, and the coil is rotated uh, in a magnetic field due to mechanical force. Generally, dynamo, if you have come across or if you have seen, dynamos are sometimes used in um, cycles, bicycles. So with a light, so when you can touch the dynamo here to the cycle's wheel, and when cycle you are cycling, then the dynamo also rotates with the friction with the wheel, and then the light will turn on. So when it rotates, to the coil rotates mechanically in a magnetic field. So due to the change in magnetic flux linked with the coil, then it produces EMF, and this EMF results in a current flowing through an external circuit, and that external circuit produces and that external circuit utilized to produce electrical energy. So it is based on the principle of electromagnetic induction, which basically says the change in magnetic flux produce the change in the rate of change of flux is right proportional to the EMF that is produced in a coil. So the working principle of electromagnetic induction is nothing but the working principle of dynamo is nothing but the electromagnetic induction. So with this we come to the end of today's interaction session. I would like to thank you all for registering in this course and for joining in this interaction session. So I hope the problems that I have solved today that will definitely help you in solving your assignment problems. With this, I conclude this session, and that's it from my side. Thank you all.